code that is working. Okay. I'll give people another minute to get here, and then I'll just get started. I just had a problem with recording yesterday on my other job, so worried about that. Okay, so quick announcements. Chapter 21 homework is due on the 26th. The chapter 22 homework is due on the 3rd. The chapter 21 quiz is today in SI, and the chapter 22 quiz will be next week on Wednesday on the 1st. And then we'll be having a test shortly afterwards, because we'll have finished chapter 23 by then. So we're going to finish off chapter 22 and start chapter 23 today. And continue on. So finishing off chapter 22, we were talking about sedimentary rocks. So some of the things about sedimentary rocks, because they pile up and build up over time, they're often used by geologists to get a better understanding of where these were deposited. So you can figure things out about what's going on, but they also record history. So things like rock color, grain rounding, grain sorting, bedding, fossil content, ripple marks, mud cracks, footprints, and even raindrop prints within the rock can reveal the rock's origin and history. And because they build up over time, certain types of sedimentary rocks can, give you information about how the earth has evolved over time. So we've used studies of the sediment at the bottom of ponds, how it's built up over the years, to study how the atmosphere has changed and pollen and such. We've also used rock buildup in caves in certain places to study the atmosphere, the carbon dioxide content, because the dripstone in caves forms in a process that involves the carbon dioxide in the atmosphere. And so you can actually study like properties of the atmosphere from the stone that forms in these caves. And there's cycles to do with, the annual cycle of rain and things like that. So the color of sedimentary rocks can be quite varied. Gray is fairly common. This indicates the rock was generally deposited within shallow, well-aerated marine waters. Things oxidize to dark colors. Organic material oxidizes to dark colors. And this is like slow oxidation. Yellow, brown, and red indicate the rock was deposited on land above sea level to the presence of abundant oxygen. Yeah, so this is less oxygen. This is lots of oxygen. You get iron oxides. So you get bright yellow, brown, and red colors. And then dark gray to black rocks contain abundant amounts of organic carbon, which is accumulated in stagnant, oxygen poor areas. If there is oxygen, that carbon goes away. It turns into carbon dioxide. And so it leaves the rocks. And so you don't get that. So these dark gray to black rocks, these form from the bottoms of bogs and things like that. So if you want to see the kind of situation that generates stuff like dark black rocks and coal and things, there is a peat bog nearby. It's called Bolo Bog. It's an hour or two away. You can go see like an active peat bog. We can also look at the grains themselves to get some information about the rock. So angular grains indicated that these sediments weren't transported very far, while rounded grains indicate great transport distances and vigorous water or wind action that wore away all the sharp edges. So conglomerate with rounded pebbles in it has to come from the bottom of streams. And so that was why it was such a big deal when they found conglomerate on Mars, because we knew that it came from the bottom of the stream, so there had to be running water. Larger grains indicate strong strains deposited in the sediments. We'll get to that in the next chapter, but basically, if it was carried, smaller particles are carried more easily by water. So the faster the water is moving, the larger the particles it can carry. So larger grains indicate that it fell out in stronger currents, while smaller grains indicate that it was very still, because a very quiet environment existed when the sediments were deposited, because otherwise they would have kept going. Sorting is the degree to which the sediments are separated according to size. Are they all mixed up together, or are they well sorted? Do we have only one size? So well-sorted sediments are composed of grains that are all about the same size. Well-sorted sediments have been carried along great distances or over long periods of time, because the sorting happens in streams. The lighter sediments are carried by, the larger particles deposited by the faster moving water, and then as the water slows down, you get deposits of lighter and lighter sediments. If they haven't traveled very far, you'll get poorly sorted sediments that are comprised of grains of vastly different sizes. And this indicates it hasn't been transported very far or very long, because the processes that sort the grains haven't gone on for very long. Now, sedimentary rock has bedding and stratification. It's layers of rock forms, and they develop as the sediment is deposited. Bedding can either be very obvious. You can see very clear bands of rock, very thick or very thin, or it can be subtle. You could have very similar layers that are very hard to differentiate. Most bedding is horizontal because most sediments come to the rest due to gravity. Usually when you see bedding at an angle, that means the rock was tilted after it formed. This is not always the case. There are some cases where sediments are laid down non-horizontally, but most bedding is horizontal. So there's some instances where there are strong wind or water currents, you get tilted bedding. This type of bedding is called cross bedding, because it also often cuts across other layers. But usually when you see tilted bedding, it happens because the rock moved. So you could have had something that was horizontal and then some force caused it to tilt up. So here are some indications of bedding. You can see the layers here. We have thick layers and thin layers. And it's fairly obvious what's going on. Now, probably the most distinctive and interesting feature you see in sedimentary rocks are the fossils they contain. A fossil is a remnant, an imprint, or any other type of trace of an ancient organism that is preserved in the rock record. The word fossil originally just meant something you dug up, which is why fossil fuels are called fossil fuels, because things that come out of the ground are fossils. But it has become focused on the remnants of living things. Now, when we talk about fossils, they're not always, the hard parts of the body of a dead thing. Those are the most famous type. Sometimes you have just imprints of things. Like you'll have fossil remains of footprints. So there's a few places where you can see dinosaur footprints preserved, where the footprints in the mud got, another layer got put down on top of them and they were preserved. In white sands, there's apparently some human footprints, which are a big deal because the dating is interesting on them and change about when humans made it to North America. But that's fossils. And so fossils are formed in a few different ways, and here's a video about that process. And sedimentary rock in general. Come on. Did I not? Yeah, okay, we're just being slow. So the formation of fossils.
Fossil formation.
Oh, shoot.
Fossil formation. At the scene of a crime, detectives look for fingerprints. The criminals are gone, but they may have left behind clues. Similarly, in the world of biology, many organisms that are now extinct left behind clues that they existed. These clues are fossils, the remains or traces of organisms that lived long ago. There are many kinds of fossils. Some are imprints left by organisms in the mud that later changed to rock. Sometimes an entire organism is found. In March 1990, for example, a whole mammoth was discovered frozen in ice in Siberia. Amber is hardened tree sap that has been preserved in the earth for millions of years. Insect fossils have been found trapped and preserved in amber. Most fossils, however, are the remains of hard parts of organisms, such as bones, teeth, and shells. Most fossils are formed in sedimentary rock. Sedimentary rock is made up of layers of clay, soil, sand, and other earth materials. Sedimentary rock usually forms in water. When an animal that lives in the water dies, its body may sink to the bottom. The soft parts decay quickly, but the bones or shells may remain and become covered by sediment. The sediments build up layer by layer. Great pressure pushes the sedimentary layers together. Slowly, through chemical processes, the sediment and bones or shells change into rock, preserving the shape of fossil bones or shells in the rock. Two types of fossils found in rocks are molds and casts. Molds are formed when an organism is buried by sediment that changes into rock. The organism decays and leaves a mold or opening. Sometimes a mold fills with sand or mud. Then the sand or mud hardens and a cast is formed.
So, and as mentioned, you can get fossils, imprints of things, and microfossils or micro remnants are a lot more interesting these days than they used to be. People used to be focused on the big dramatic bones, but now, things like pollen and stuff are also very useful. So the reason that you get fossils primarily in sedimentary rock is because the processes that form, igneous rock and metamorphic rock are generally involve very high temperatures and pressures, so they just destroy the fossils. So usually fossils don't survive the transformation of metamorphosis. Igneous rock is coming out molten, so you're not going to have a fossil survive that. The process is destructive to fossils. So as we've already learned, igneous rocks formed by the crystallization of magma that generally forms deep within the earth. Sedimentary rocks are deposited at or near the surface of the earth. What about in between? Metamorphic rocks form in conditions below where sedimentary rocks form and above where igneous rocks form. They're in the middle. And metamorphic rock forms when pressure and temperature conditions that are different from where the rock originally formed cause the rock to transform to a new rock type. because if it was in its original pressure and temperature conditions that it formed, it wouldn't really change. The pressure and temperature conditions lie between the other two rock types. That rock can transform. So we saw some metamorphic rock in the lab on last week. Yes. No, on Monday. Sorry, my brain is shorting. But yeah, we saw them in the lab. We just did. And those, one of those had both heat and pressure. That's the one with the bands. The other one primarily just had heat. So metamorphism is the conditions in the earth that result in the changing structure and mineral contact of a solid rock without melting it is metamorphism. So any sort of rock can be metamorphosed, igneous, sedimentary, or even other metamorphic rocks. And the agents of metamorphism are heat, pressure, and chemically active fluids. And by chemically active fluids here, we mainly mean water. So heat and pressure break some of the mineral bonds in the original mineral, with the fluid serving to allow the movement of the ions from one place to another. So basically, minerals can transform and rearrange. And be restructured. So when we talk about metamorphism, we talk about a parent rock, the rock you started with. So in addition to heat, pressure, and fluid activity, the composition of the parent rock helps determine what metamorphic rock forms. So, for example, my box of metamorphic rocks, here we have a rock this is granitoid gneiss. This was formerly granite. Here we have white marble. This was formerly limestone. And you can see they're quite different, though probably the conditions were a little different as well. And metamorphism can also cause certain minerals to leave, sort of dissolve out of, certain elements to exit other minerals and form new minerals. This is why often a lot of the gemstones people like form in metamorphic rock. So you have some minerals, some rock that's got a lot of aluminum in it. That's fairly common. It gets heated up. The aluminum and some of the oxygen can exit and form things like sapphires or rubies and other corundums. So the parent rock is, what you have to work with. So the overall process of metamorphism can change both the texture, the crystal size, and the mineral composition of the parent rock. So marble, for example, the big changes in texture. Going from limestone to marble, that changes texture. It's the same mineral. Or it could only change one of these characteristics of the parent rock. While other ones like gneiss or that striped rock you look at that had both texture and mineral composition change. Generally, if you start with a rock that's made of only one mineral and it metamorphoses, it stays that mineral. Not always the case, but that's generally the case. It's much more likely for mineral composition to change if you have mixed together minerals, because then some ions can move from one mineral to another and change both of them. Or you can sometimes get things where some ions will leave the minerals and form new minerals, like when you get sapphires or something like that. So here, for example, metamorphic rocks come in two varieties, foliated and non-foliated. Foliated rocks are under asymmetric pressure. They have more pressure in one direction than others. So everything gets sort of squashed. And you see elongated crystals. And you also see, that's also where you get those bands and layering. But, so here we have shale will turn into slate. And the key minerals are clay, quartz, mica, and cordite. And it's fine grains and slaty cleavage. It's very wide, not flattened. Shale and basalt and slate could turn into schist, which has chlorite, plagioclase, mica, and garnet. It's coarse grains and it's well foliated. Shale, granite, slate, and schist can turn into gneiss, which has plagioclase, garnet, kyanite, and sillimanite. It has coarse grains and light and dark colored bands. So that banded rock we have. This banded rock that you looked at is nice. I think so. Yeah, this is biotite gneiss. This also used to be a granite. So this used to be granite. And got squished into layers. This used to be limestone. And this is non-foliated and this is foliated. Now, if you have limestone, the metamorphic rock it turns into is marble. So this and that pink rock you were looking at in the lab are both marble, started as limestone. The key mineral is calcite. You get coarse interlocking calcite grains. Sandstone goes to quartzite. Is there a quartzite in here? So this is quartzite that started as sandstone. You get fine to coarse interlocking quartz grains. It's hard to see in this because they're small. And then shale, basalt, or any other fine grade rock can turn into hornfells, which tends to have mica and quartz in it and has fine grains and variable composition. Are there any hornfells in here? No. So I think this is yeah, I don't see any hornfells in here. That's not a very green rock for all that it's supposed to be. Okay. So in general, if the parent rock only contains one mineral, the metamorphic rock will also be composed of that same mineral. Usually, if it's only one mineral, it's unlikely to change. But, so for example, limestone metamorphoses into marble. And both of these are made of calcite. But limestone has more separated particles and smaller crystals, while marble has bigger crystals and more bound together particles, bound together crystals. There's a lot. The structure of it has changed, but not its chemical composition. And so marble makes a much better material for statues than limestone. So this is limestone. It's much more irregular, while marble is much sort of smoother and continuous. And all the fossils in the limestone get destroyed as it turns into marble. Another example of this with a rock containing only one mineral is sandstone to quartzite. Both sandstone and quartzite are composed of silicon dioxide. But quartzite ends up a much tougher, stronger rock than sandstone because the recrystallization binds all the particles together because they grow into each other. All the crystals grow into each other and they're interlocking. So quartzite's much harder than sandstone. And when sufficient heat and pressure is applied to sandstone, all of the grains will fuse together to form the very resistant rock quartzite. And if the parent rock is composed of several minerals, the process of metamorphism can change to a new suite of minerals. And these new minerals are formed in response to the escalated heat and pressure conditions. So shale, for example, is a very fine-grained mixture of several minerals: quartz, clay, mica, and chlorite. And depending on the degree of metamorphism, shale will be progressively changed into slate, schist, or gneiss. So you get shale, slate, schist, gneiss. And sort of a sequence. And this happens as you increase metamorphism and temperature. You get different amounts of, you get different minerals. And then eventually, if it gets too hot, it all just melts. So, quartz goes all the way through. Phosphate, chlorite might, these show up later. Garnets show up, but they don't usually make it into the gneiss, and so on. Different minerals at different levels of metamorphism. So here's sort of this process, shale, slate, rhyolite, schist, gneiss. Striking gneiss is sort of the end state. And there's three basic types of metamorphism. Contact metamorphism is when magma rises up through existing rock and heats it up. So contact metamorphism, when magma comes direct contact with the parent rock, it cooks it, gets it very hot, and that causes it to metamorphose. And so the changes, contact metamorphism, you're mainly dealing with high temperature, but not high pressure. Immediately next to the magma, you get intense metamorphism, which forms very coarse-grained crystals. And as you move away from the magma, the rock gets progressively finer grained. And a contact metamorphic zone occurs when parent rock gets intruded by molten magma, when molten magma moves up through the parent rock. That's how you get stuff like marble. It's primarily formed by contact metamorphism. Shear metamorphism is primarily pressure. When the intense pressures that exist along active fault zones where rocks slide past each other, you get mechanical deformation and recrystallization from the heat, the pressure, heat, and movement of fluids as rock units slide or shear past one another. This is less common. We're not going to talk about it quite as much. We're going to focus mainly on contact and regional. Regional metamorphism affects extremely large areas and is caused by a combination of both high temperature and high pressure. This is like when mountains are forming. You get rocks that are buried very deep and squished very hard. So they're both hot and highly pressurized. And most areas that are affected by regional metamorphism are areas undergoing intense deformation due to various mountain building processes. So this is common at convergent plate boundaries. Shear metamorphism is just less common. So there's a video about the difference between contact and regional metamorphism.
There are two types of metamorphism that occur in nature. The first type is called contact metamorphism, and the second is called regional metamorphism. So let's talk a little bit about the difference between these two. Now, imagine you have the surface of the earth here, and you can see some trees, and these colors here, these are layers of rock underground. And so I'm going to show you how contact metamorphism works. The reason it's called contact is because it involves existing rocks coming into contact with really intense heat, which is generally provided by lava or magma. So imagine that one day an intrusion of magma forces its way up through these layers of rock. Now, all of the existing rock are going to be burned by the heat of the magma. So all along the edge of this magma, shown here in orange, you're going to have rocks that have been burned by the heat of the magma. That burning causes them to change or metamorphosize into something new. So anywhere you see the orange, you're going to have some metamorphic rock. This is caused primarily by heat. Let's fill this in on our flowchart. Okay, so the first type is contact metamorphism, and this is caused by contact with heat. Whenever a rock comes into contact with magma or lava, it is burned or metamorphosized by that heat. But let's talk about the second type, regional metamorphism. Now this one is going to be more from pressure. So let's imagine that I have a plate boundary here, a fault, a crack, and that these two plates are coming together. So it's a convergent plate boundary. Well, as you can imagine, in the middle here, there's going to be immense pressure, and that pressure can cause the rocks trapped in the middle to become metamorphosized. So all along this boundary, you'll find metamorphic rocks. Again, this is different from contact in that it's not so much about the heat, it's more about the pressure. Let's take a look at what we see here. This is a typical progression of metamorphism that occurs. Starting with the sedimentary rock shale, if you add heat and pressure, it will metamorphosize to slate. If you add more heat and pressure, it will become phyllite, more, and it will become schist, even more, and it will become the metamorphic rock gneiss. Take a look at that gneiss sample down there. You'll notice it has bands of minerals. That's a result of the intense pressure. Now, if you were to take gneiss and add additional heat and pressure, it would likely melt into magma or lava, and then it would become an igneous rock. So gneiss is generally the extent of metamorphism that we see. Let's go back to our flowchart. So our second type of metamorphism is called regional metamorphism, and this is caused primarily by pressure. Of course, all of this is summarized in your reference tables on the metamorphic rock chart on page 7. You'll notice type of metamorphism, composition, what minerals are involved, how big the crystals are, whether it has banding or not, the names of the rock, and the map symbols. And of course, we'll learn lots more about this chart in detail in the coming days. Thanks.
So, metamorphic rock and regional metamorphism is under enormous pressures, and that can cause foliation. What it causes is the grains to all align with each other. And they also can get sort of squished. And it causes prominent layering in metamorphic rock. And only rocks that are metamorphosed under intense pressure will exhibit this foliation. So metamorphic rocks that form primarily due to high temperatures will not have foliation. And so the progressive patterns of foliation that develop in metamorphosed rocks serve as a good example of foliation types. So if you start with shale, so this is your starting material. This is shale. Then you can become slate, which is so this is slate, which is slightly metamorphosed shale. Then, so that's slate, you get slaty cleavage, you get much flatter, more clear layering, but it's still pretty similar looking. Then you can get chists. So 27. Well, I'm not going to take this out of its little package, but here's a chist. And then lastly, you can get gneiss. This form of all the layers. The various minerals separate out. So gneisses form under intense regional metamorphism and display banding. The more intense the metamorphism, the larger the crystals, but the less distinct the foliation. So here's about how metamorphic forks form and how foliation works. That is not what we're supposed to have.
When sedimentary rocks form, they pile up and create layers of rock. Once these layers build up, they begin to put tremendous pressure on each other. This pressure, combined with heat from Earth's interior, is going to change these rocks into metamorphic rocks. This change can happen in one of two ways. Regional metamorphism, which means it happens over a large area, so the pressure is very intense, or contact metamorphism, where the pressure is less intense since the change happens with contact with magma. Shale is a sedimentary rock that through increased regional metamorphism will change to slate, then to phyllite, then to schist, then to gneiss. Through increased heat and pressure, the minerals in the rock shale are going to change into different rocks. A few things will happen in metamorphic rocks, including that the minerals will recrystallize since they are exposed to new heat. Also, this causes foliation, which is where the minerals begin to line up and eventually form bands of the same minerals. Not all regional metamorphism is going to have foliation. For example, bituminous coal, when it changes into anthracite coal, it's not going to have foliation. The second type of metamorphism is called contact metamorphism, where various rocks will be changed by the heat from nearby magma. For example, the rock hornfels will only be made through contact metamorphism. Other metamorphic rocks that don't have foliation but can be formed by both regional and contact metamorphism are quartzite, marble, and metaconglomerate. So to summarize the rock cycle, when rock that melts into magma cools and solidifies, it becomes igneous rock. Those rocks can be broken into sediments and eventually they get deposited and buried. They then compact and cement together into sedimentary rocks. Eventually you have layers that build up, and through heat and pressure, the crystals reform into metamorphic rock. With enough heat and pressure on the metamorphic rock, it can then melt back into magma, and if it cools, well then you start the process over again with igneous rock. That's all you need to know for today. Tomorrow we are going to complete a rock cycle as part of our final work. But for today, please make sure to answer.
So, here's a slate bed, here's schist, here's gneiss. This is sort of the progressive process of metamorphism. So that's the end of chapter 22. Minerals are composed of what? Two pure substances. So you can have, there's, but that was a weird question. I'm not remembering exactly how to answer that really quick. But minerals are, they're solid, inorganic, crystalline substances. They're crystals. They can be pure elements if necessary. They're solid, inorganic, naturally occurring crystalline substances. A mixture of minerals forms a rock. A particular rock that has commercial value is referred to as an ore. The two most abundant elements in Earth's crust by mass are silicon and oxygen. The most abundant mineral family is called the silicates. The most common example of the mineral family talked about in number 5 is feldspars. The most common silicate mineral, followed by quartz. The feldspars are the most common. The three most common non-silicate mineral families are the oxides, the carbonates, and the sulfates. These are sulfates as opposed to the sulfides. Another common one is the sulfides. The most unreliable physical property of a mineral to use in its identification is color. The arrangement of atoms and ions in a mineral is referred to as its crystal structure. A mineral's resistance to scratching is called its hardness. The ability of a mineral to split along flat planes is called cleavage. The Mohs hardness scale ranks mineral hardness, with the softest mineral having a value of 1 and the hardest mineral having a value of 10. And this is just a relative scale. Use an absolute hardness scale. The Mohs hardness, like the jump from 9 to 10 is much bigger than any of the other steps, for example. A mineral that breaks in an irregular way is said to have fracture. The color of a mineral's residue left on a black or white plate is called the streak. It's the color of the powder of the mineral. The two main types of mineral luster are metallic and non-metallic. The density of a mineral compared to water is called its specific gravity. The three classes of rock are metamorphic, sedimentary, and igneous in reverse standard order. The three of the three classes, the one that formed first on Earth is the igneous rock. Molten rock found on the Earth's surface is called lava. Molten rock that's in the Earth's interior is called magma. Igneous rocks with small crystals due to rapid cooling are called extrusive rocks because they formed outside the Earth. Igneous rocks with large crystals due to their formation in the Earth's interior and their slow cooling are called intrusive rocks. The concept of geological processes have been occurring for a long time and continue to occur today is called uniformitarianism. And the series of changes rocks undergo due to various physical and chemical processes is called the rock cycle. The energy for forming igneous and metamorphic rock comes from the movement of tectonic plates. Igneous rocks that are dark and contain a high percentage of magnesium and iron are called mafic rocks. Igneous rocks that are, or sometimes basaltic, but the technical term is mafic. Igneous rocks that are light in color and contain a high percentage of silica are called felsic rocks. They're also sometimes referred to as granitic because they're like granite. The largest pluton that crosses many layers of rock is called a batholith. A vertical igneous intrusion into the surrounding rock is called a dike. A horizontal igneous intrusion into the surrounding a vertical igneous intrusion into the surrounding rock. If it's just along a crack and thin, it's called a dike, but that's generally, it's called discordant. And horizontal ones, if it's flat and thin, that's called a sill. Yeah, that's a sill. Horizontal igneous intrusion cutting through the surrounding rock is called a sill. And the ones that don't the ones that cut through layers are called discordant. The ones that don't are called concordant. And a fairly large igneous intrusion that does not cut across layers of rock is called a laccolith. It sort of blisters up layers above. An explosive volcano is one in which its lava contains a large amount of silica and water, dissolved water. So high silica content. A quiet volcano is one where lava will contain a lot of iron and magnesium, but little silica. So and it will often have less gas and water in it as well. Lava with high viscosity contains a lot of silica and has a fairly low temperature. Quiet volcanoes usually expel basaltic rock, basalt, high temperature, low viscosity magma, lava. Type of volcano that's fairly short and has steep sides is a cinder cone. Very large and have alternating layers of ash and lava is a stratovolcano or composite volcano. Type of volcano with gently sloping sides but erupts frequently is a shield volcano. The process of transforming sediments into rock is called lithification. The two general classes of sedimentary rock are clastic and chemical. Plastic are made from debris. Chemical is made from the dissolved minerals. The two types of chemical sedimentary rock are inorganic and organic. One involves living things, the other doesn't. That's the organic one involves living things. The class of rock that can contain fossils is basically all sedimentary rock, is most likely to have fossils. This inorganic chemical sedimentary rock is less likely to have fossils, but it still can happen. The two primary agents of metamorphism are heat and pressure. The three types of metamorphism are contact, shear, and regional. And if a metamorphic rock contains banding, we say it is foliated. So that was chapter 22. Let me open up chapter 23. And we can talk about surface processes. Stop sharing and share again because of this stupid bug. So surface processes. These are processes on the surface. So we'll talk about the difference between mechanical, we'll talk about weathering, the difference between mechanical and chemical weathering. We'll describe the chemical changes that occur in chemical weathering. We'll look at the action of the primary agents of erosion, streams, glaciers, wind, and waves on the various surface features of the Earth. So weathering is the breakdown of rock, erosion is the movement of sediment to another location. We'll trace the movement of water in its various forms through the water cycle. We'll talk about the distribution of Earth's water. We'll look at the challenges to a clean and usable water supply. We'll describe the effects of waves on shorelines. We'll talk about the topographic features of the seafloor. That's sort of the general thing. So within the context of geologic time, the Earth's surface is a very dynamic area. Nothing is permanent. It changes very quickly compared to other parts of the Earth. And it's as soon as rock is exposed to the Earth's surface, various weathering processes begin to break it down and destroy it. And due to various weathering processes, erosion and gravity, high places on Earth are constantly being worn down by the transportation of sediment to low places in a process that is known as gradation. So gradation is the leveling out of the Earth caused by the movement of sediment, as opposed to just, the movement of sediment is erosion, but the leveling out and movement of sediment from high to low is called gradation, because it's leveling everything out. So the process of the disintegration or decomposition of rocks is weathering. So environmental agents can cause the physical disintegration. So if you were to physically disintegrate a rock, you would hit it with a hammer to break it into smaller pieces. And the chemical decomposition of rock. With this, you would expose it to something that would dissolve away certain parts of the rock. Of rocks and minerals at or near the Earth's surface. The weathering is generally a slow but powerful force that eventually breaks down even the most resistant materials. So in places where we live, like where we live, where we get lots of freeze-thaw cycles, weather rapidly switches between freezing and not freezing, we get a lot of physical disintegration caused by that. In other places where it's warm and wet, you get lots more chemical decomposition. So the overall climate determines the rate of weathering and the type of weathering that occurs. So mechanical or physical weathering is the breaking down of rocks and minerals into smaller pieces, disintegration, without changing the chemical composition. You're not dissolving part of the mineral, you're not transforming the mineral in any way, you're just breaking it into smaller pieces. The most common process of chemical weathering around here, physical weathering around here is frost wedging. This is one of the most common forms of physical weathering caused by the expansion of freezing water in joints or in fractures, joints, or cracks in rock outcrops, causing those cracks to get bigger and eventually pass through the rock and break it. Because water increases in volume about 9% during the process of freezing, which is why you shouldn't freeze a sealed rigid bottle because it will shatter. And this force will expand the fractures and loosen the fragments of the rock. So here's a video about the process of frost wedging and how the rock gets broken down.
Believe it or not, the rolling countryside of Cornwall in southwest England used to look more like the Himalayas or the Alps. Mountains don't last forever. They gradually wear away at a rate of about 10 centimetres every 1,000 years. So all that's left in Cornwall today is a series of domed shapes, giving the landscape its rolling appearance. Changes in temperature from day to night and the expansion of freezing water cause rocks to wear away. When water enters a crack in a rock, it expands as it freezes overnight. When the ice turns to water and freezes again, it forces the crack open a little more. As the water seeps even further, the crack widens. This freeze-thaw action is repeated. It eventually causes pieces of rock to break off. They fall down the mountainside, where they lie as pieces of jagged rock known as scree.
So here's an example of frost wedging, various rocks broken off by that frost wedging. Another example of frost wedging that you've probably encountered around here is potholes. You get lots of potholes because of frost wedging. Another thing that can exist is permafrost. So certain places in the world, the soil is permanently frozen under the surface, but the upper layers can melt. So the topsoil can thaw, resulting in a wet, spongy conditions. And this freeze-thaw cycle contributes to physical weathering processes. And also that upper layer of the permafrost can sort of slowly flow as it melts. But physical weathering can also be promoted by biological activity. Roots can grow into cracks and press them out. Another form of physical weathering that happens in warmer places, but with salt, is the growth of salt crystals can also widen cracks. But action by burrowing animals and by plant roots that grow and expand rock crevices can lead to biological weathering. There's also chemical weathering from living things, because certain living things generate acidic things that break down the rock. So here's a short video about permafrost and why the loss of permafrost is such a big deal. It's because it's trapping a whole bunch of stuff that we really would like not to be released.
Anna, we are in the northeast of Russia, deep inside the Arctic Circle, where outside at the moment it is hot enough to sunbathe. But I'm inside what is called a permafrost cave. Permafrost is the permanently frozen layer of soil that sits beneath a quarter of the northern hemisphere. And as our planet warms, and the Arctic is warming much faster than the rest of the planet, this layer of soil is beginning to thaw. And that means that the billions of tons, hundreds of billions of tons of carbon trapped inside is released. I'll show you what that means. These roots are essentially plants that were frozen in the soil at the time when the mammoths were roaming the grasslands up above. But as this stuff thaws, this decomposes and greenhouse gases are emitted into the atmosphere, methane and CO2, and that warms up the planet further. And that is why this permafrost and what happens to it is really just as important in terms of climate change in the Arctic as the melting ice caps and rising sea levels.
So that's permafrost, but there also is biological weathering. So here is a short video about the process of biological weathering, how living things can help increase the rate of weathering.
So looking around us here, this is an excellent example of just how weathering happens, whether through biological or other physical means. So we don't have a lot of, well, there may be a little bit of chemical weathering going on here with rainwater and stuff, but this is some fairly stable sandstone. So we got little sandstone surfaces in here still visible, but we were just marveling at how thick and dense the moss is along the side of this cliff. Okay, you can see as I push into it just how plush it is, which means that we've got generations and generations of moss that's been growing, finding every little tiny nook and cranny in that rock and forcing those cracks just a little bit wider. Eventually yellow birch seeds are able to fall onto the moss, take purchase in the moss itself, and then work its way into any cracks that happen to be wide enough in the rock. Like this tree is on there. I could probably climb that sucker, and it's only about the diameter of my leg. Then eventually, as those cracks widen open, we get rocks that are falling off here, big cracks in between the rocks here, and then entire canyons that I could literally walk into here, that form between the rocks as frost wedging speeds things along and other processes encourage, as my pack gets stuck on the rock, as other processes encourage that kind of breaking open and weathering of the rock, all in place, in situ as we say, and eventually gravity will take hold and knock big chunks of those rocks off, and then other processes of erosion can get involved as well. But in the meantime, this is a great nursery of mechanical and biological weathering.
So that was physical weathering. Physical weathering is pretty straightforward. Various processes make cracks bigger. Either something gets wedged in the crack and gets bigger, grows. That's the biological one. You can have freeze-thaw cycles. You can have something like you can just have like wind carrying sand past, wearing away surfaces, things like that. Chemical weathering is the process where the chemical composition of rocks or minerals changes, and this is principally through reactions with water. Certain minerals can dissolve in slightly acidic water. So water and temperature are the two most important factors in chemical weathering. If there's not a lot of water, you don't get a lot of chemical weathering because you need water to dissolve things in. If it's cold, it's harder to dissolve things. If you want to dissolve more stuff in some water, you heat it up. So water or groundwater is slightly acidic from several causes. It absorbs carbon dioxide from the atmosphere, gets slightly acidic. It'll also pick up stuff in the ground and become slightly acidic from living things. And that can dissolve away things like limestone or other minerals more slowly. And chemical weathering is thus more efficient in hot, moist, tropical climates. And the most commonly chemically weathered rock is limestone, just because it readily dissolves in slightly acidic groundwater. It's just easy to dissolve. If you make the groundwater a little bit acidic, which the carbon dioxide in the atmosphere does. As you see, some of the most dramatic chemical weathering in hot, moist climates. So Southeast Asia, that area. If you've ever seen those bays with those really dramatic pillars covered in trees, that is a really dramatic case of chemical weather. These really tall, thin islands that you get in certain bays in Southeast Asia, southern China, places like that. So limestone is made largely of the mineral calcite, but we get this also around here. It happens around here as well. Wherever there's limestone, you get chemical weathering. And normal rainwater will react with carbon dioxide in the atmosphere to form a weak solution of carbonic acid, which is H2CO3. This is why all carbonated drinks are acidic, though some carbonated drinks also have other acid added to them, like Coke has phosphoric acid added to it. I think it's phosphoric. It has another acid added to it specifically. And you also might have citric acid and other things. But, Coke is a lot more acid than you get from just the carbonation, because there's another acid dramatically added. But, H2O plus CO2 gives you H2CO3. So just carbonated water will be slightly acidic. And the more CO2 the water comes in contact with it, the more carbonic acid is formed. And as it percolates through the soil, it can pick up even more carbon dioxide and other acidic compounds released by living things like bacteria and lichen and things like that. The carbonic acid, as it comes in contact with calcite and limestone, they react. And, you get calcium bicarbonate, which readily dissolves in water and gets carried away in solution. Calcite is, calcium carbonate. It reacts with the carbonic acid and you get calcium bicarbonate. This gets carried away in solution. It can then come out of solution when the water evaporates away, forming like stalactites and stalagmites in caves. Most of the chemical weathering in limestone occurs along fractures where the most water flows, and this forms large caverns. So most caves that people go to look at are limestone caves, because the water flowing through them forms nice big, dissolves away limestone and forms caverns. The cavern ceilings can collapse, causing sinkholes. And when you have limestone topography with lots of caves in it, it's called karst topography. And it's very common. About a quarter of Illinois is covered in karst topography or something like that. A similar amount of Indiana. So here's a short video about karst topography. This is from the University of Illinois. So this is a chimney located in the lunchroom in the Illinois Caverns in Monroe County. You can get enormous cave systems. The biggest cave system in the world is a limestone cave in Montana? I can't remember now. Maybe in Washington. My name is Man with Kevin.
Hi, my name is Sam Pano. I'm with the Illinois State Geological Survey, and I'm a senior geochemist.
Oh, it's in Kentucky.
Under the Prairie Research Institute, which is part of the University of Illinois. And in my job, I do a lot of investigations of karst areas, and I should probably tell you what karst is. About 25% of the world sits on karstified carbonate rock, like limestone and dolomite. And in Illinois, 25% of the bedrock is limestone and dolomite, with about 10% of the area having karst features. If you have carbonate rock, which is soluble in rainwater, it dissolves in rainwater, soil water, and so on. So basically, all the rocks, all the bedrock in Illinois and the entire world are fractured to some extent. And when the rainwater seeps in, or surface water, it begins to dissolve this rock. The process takes thousands of years, tens of thousands of years, millions of years. What occurs is as the fractures get bigger and bigger, then the water can seep into the bedding planes, just fairly flat-lying layers of limestone, and create caves. And the caves can be quite extensive. For example, in southwestern Illinois, there are caves that extend for 15 miles with passages that are 30 feet in diameter and rivers running through the cave. So this is the kind of areas we study.
And well, the longest cave in the world is not that far away from here. And that is Mammoth Cave. That's in Kentucky. Okay, so it's about 5.5 hours away. But it's the longest cave in the world, and it runs for hundreds of miles. Like over 400 miles long. And they don't know the full extent because exploring caves is hard and dangerous. Exploring the furthest extents of caves can get very hard and dangerous, and they're often flooded because they're formed by water. So you have to be very careful about it. So there's often places, you just don't know how far it keeps going. Here's a sinkhole forming from a collapsing.
Oh yeah, you said they move it, John.
Yep, I got it.
Water.
I got it.
It's moving that much. Oh, that's gone right there. Is it right there?
And you can watch this set of trees just go. So there's a
Trees falling.
underwater cave collapse.
Look over there, John, on pad 3. Well, let's get a read. You had a 1-foot wave hit it that way, you know, coming back a little bit.
So figure out where we were. So chemical weathering is most rapid in areas with high temperatures and abundant moisture. In very cold regions like polar regions or very dry regions, deserts, the chemical weathering is relatively sluggish. Let's stop there for today. I'll see you all next week when we're going to finish off chapter 23. So. That all needs to move. Okay, that's. What do I want to do? Let's see. Oh, okay. Well, that's done then. Oh, that's not great.
Super hard. Very unfun, traditionalist people who expected to be rewarded for the way they lived. So became unable and unwilling to cohabitate with people outside of that group. That's why they all got on a boat together and they built a safe space on native lands. And lots of this American Christianity isn't actually based on traditional theological history and thinking, but this pioneer culture, this building it up culture, this Puritan culture that's heavily whitewashed and layered. Evangelical Christianity is imperialist Christianity. This idea in right or wrong, good or evil, and everyone should be on the side of good or else you're on the side of evil. To them, godliness is converting or destroying.
Oh.